Chemistry Chapter 20, Theory Video 8, Combining Half Cells. So now we learnt about the standard electrode, standard hydrogen electrode, and then we discussed how it can be connected with another or combined with another half cell to find out the E standard values. So now we are going to figure out how it can be done and what kind of reactions would be involved in the process. In order to measure the electrode potential relating to the half equation, Cu2 plus aqueous plus 2 electrons becomes copper solid. So once again remember, the ions and electrons would be on the left hand side because this refers to the reduction equation. We place a pure copper rod in a solution of Cu2 plus aqueous ions. So Cu2 plus aqueous ions means some chemical that contains copper ions. For example, copper 2 sulfate ions. A solution. This copper 2 plus copper system is called a half cell. So that means, in reality, what it means is that there is in here, in this particular system, there is this metal copper piece and then copper ions here. So that is what it refers to. So it is a combination of the iron as well as the metal. So here what we need to understand is that that some sort of equilibrium is generated, and equilibrium would exist between the copper ions and the copper metal. So that means from this copper rod, right, copper ions would go into the solution, and from the solution copper ions would come to the metal, and it will coexist in some kind of a equilibrium. So that is what basically you need to understand, right? So then we use the following standard conditions to make the half cell. So in this half cell, these standard conditions need to be met. Copper ions have a concentration of 1 mole per cubic decimeter. So this blue color solution of copper sulfate needs to have 1 mole per cubic decimeter concentration of solution. Now when you answer 52 page paper 52, you would have to know how to make the standard solutions. Right, you have to have that general background information. You need to have a thorough knowledge about that. So please remind yourself how, when you did practicals, how you made the standard solutions. So to remind you, I will tell you what you do is you take some amount of initially what you do is you weigh 1 mole of copper sulfate. How do you find out 1 mole of copper sulfate? One of the ways of doing it is 1 mole of copper sulfate can be taken. That is, you find the molar mass of copper sulfate by taking the mass of copper, sulfur and oxygen and then adding them all with the proportions of the atoms involved in formation of copper sulfate, and then you take it in grams, you measure that, you put it into a flask which can hold 1 liter or 1 cubic decimeter of liquid. Then what you do is you fill it up to about 500 cubic centimeters, and then you dissolve all of the copper sulfate, and then you fill it up to 1000 cubic centimeter or 1 cubic decimeter mark, and you will have a solution of 1 mole per cubic decimeter solution. Then coming back to the standard conditions that should be involved in this half cell are: the copper ion should be in 1 mole per cubic decimeter concentration. The temperature should be standard 298 Kelvin or 25 degrees Celsius, and the copper rod must be pure. So there cannot be any impurities on it. if we connect two half cells together, we have made an electrochemical cell. So obviously you cannot connect another similar half cell, because then the values wouldn't be different, right? So there wouldn't be any voltage being generated. So it has to be a, if you are connecting with copper metal and copper solution with another copper metal and with the same conditions, then there wouldn't be any voltage generated. There has to be a difference in their reactivities as well as the standard values when measured. We can measure the when after you take this electrochemical cell, then there is a voltage generated. This voltage can be measured. Figure 20.7 shows a copper iron and copper half cell connected to a zinc iron and zinc half cell to make a complete electrochemical cell. So let's go to this figure 20.7 and see how it is done. So here you have the electrochemical cell. So in here you have this is the copper iron copper metal half cell, and here you have the zinc iron zinc metal half cell. All right, so now what you need to understand here are the parts of this. So this copper rod is there in copper solution, zinc rod is there in zinc iron solution, and it is connected. These two copper rods and copper and the zinc rod are connected with high resistance voltmeter using wires. And then for the ions to move, you have to have a salt bridge. As you can see here, there is a salt bridge. This is the salt bridge. So this salt bridge allows for the ions to move, right? It will allow the ions to move. We will learn what it is made up of. So it has to be made up of a porous material which allows the ions to move. So when this if you have a doubt as to why is a salt bridge needed, because if you connect only with one wire, the circuit is not complete. It has to be for the circuit to complete, there has to be a full circle, right? So that circle is connected through here, right? Because originally there was no connection here. There was no connection, right? So if I'm to show you again, what happens is, as you can see here, this is connected here, right? So but for the current to pass through, there has to be a connection. That means this needs to be there has to be a connection here. So how is it connected? It is connected by using this salt bridge. That's how it is done, right? So this is actually this makes the connection here, but because it is the ions that are involved, ions have the ability of moving. I hope you understood that. Well, moving on. We use these two half cells to produce the electrochemical cell, and there would be a voltage generated. This voltage can be measured. So these half cells are connected using a wire connecting the metal rod in half cell to a high resistance voltmeter, right? The electrons will flow around this external circuit from the metal with this is very important, metal with the more negative or less positive electrode potential, right? More negative or less positive electrode potential to the metal with the less negative or more positive electrode potential. Now you would understand why if you connect a copper half cell with another copper half cell, why it wouldn't move, because the electrode potentials are not different, right? So the electrons would move from more negative electrode potential to the less negative or more positive electrode potential. So the negative to positive. A salt bridge to complete this electrical circuit, allowing the movement of ions between the two half cells, like I said earlier. Right? Through the salt bridge you cannot pass electrons, because for electrons to move through there has to be a metal medium. A salt bridge can be made from a strip of filter paper or other inert porous material, so that it should not take part in the chemical reaction, soaked in a saturated solution of potassium nitrate. This point, a lot of people forget this point. So you have to remember this potassium nitrate. I myself forgot this during an exam. I could not remember this at all. Everything else I remembered, but I forgot this point. Because I forgot that point, I lost some really good marks, because I couldn't go to the next stages without potassium nitrate. So you have to remember all of these details. Right. So you know how the half cells are connected now. So we can figure out the voltages in here now. When so the half equations are going to be Cu2 plus aqueous plus 2 electrons giving copper, and then zinc ions take electrons to give zinc. Right? So the voltages are plus 0.34 volts and negative 0.76. So from where to where will the electrons flow? Then we know that zinc ions are more difficult to be reduced. Right? Copper ions are easily reduced because it has a positive value, and zinc ions have a more negative value. Right? So copper ions will accept electrons from zinc, and zinc will lose electrons to copper half cell. So that is what happens. Right? So I hope you understand that the relative values, that is the plus 0.34 in copper and negative 0.76 volts in zinc half cell, it shows us that zinc ions are more difficult to be reduced. That means zinc metal will easily become zinc ions, and copper ions will easily become copper. Right? So then what does that mean? For copper ions to easily become copper, it needs 2 electrons. So from where does it take electrons? So from zinc. So zinc will give the electrons to copper half cell. Right? So the electrons would flow from zinc to copper. So I hope you understood that. Here you have to understand the electrons flow from, read this part, the electrons flow around the external circuit from the metal with the more negative electrode potential to the metal with less negative or more positive electrode potential. So so it is more positive, more negative one is zinc. So from zinc to copper, electrons would move. Right? Half equations can be used to show us the contents of half cells. A half cell does not have to be a metal or metal ion system. We can construct half cells for any half equation written. For example, Fe3 plus aqueous plus E minus, Fe2 plus aqueous, chlorine plus 2E2Cl minus, manganate ions plus H plus, becoming manganese and water. So all of these electrons are on the left. Note that the oxidized species having the high oxidation number is always written on the left hand side. And the reduced form on the right hand side. I hope you understood. I will give you the note in the next video.